Your head is aging faster than your feet. Not as a figure of speech, as a measurement. Place two of the most accurate clocks ever built 1 millimeter apart, about the thickness of a grain of sand, and they immediately begin to disagree. The higher one runs faster. In 2022, physicists measured exactly that. So time does not run at one rate. It runs at every rate, everywhere, depending on where you stand. Which leaves a question with no comfortable answer. If every perfect clock gives a different answer, which one is telling the truth? Relativity says none of them. There is no universal clock. There is no shared present moment. What is happening right now, somewhere else in the universe, is not a fact. It depends entirely on how you are moving. And then it gets worse. Physicists tried something close to absurd. They asked a single equation to describe everything that exists. Every galaxy, every atom, everyone alive, the entire universe at once. They wrote it down in 1967. Time was not in it, not hidden, not waiting to be found, simply absent. The equation describes a universe that does not change, and in nearly 60 years, nobody has fixed it. Tonight, we follow time until it disappears. And then we visit the laboratory 3 weeks ago, where somebody built a universe in a jar and watched it invent its own time. "20,000 kilometers above your head, in vacuum, in silence, a metal box the size of a car is falling around the Earth. It has been up there for years. Sunlight on one side, absolute dark on the other. Inside it, shielded and temperature-controlled, an atom is being counted. There are dozens of these boxes, circling the planet twice a day. Your phone listens to several of them at once. Each one broadcasts the time on its own clock, along with where it is. Your phone compares the signals, works out how long each took to arrive, and from those slivers of delay, calculates the ground beneath your shoes. The whole system runs on timing. Light travels roughly 30 centimeters in a billionth of a second. So an error of 1 microsecond in that satellite's clock puts you 300 meters from where you are standing. Those clocks have to be perfect. They are among the most accurate objects human beings have ever built. They are also wrong, every one of them. Predictably, measurably wrong in 2 directions at once. The first error comes from speed. Those satellites are moving at nearly 14,000 kilometers an hour, and a moving clock runs slow. Not appears to, runs slow. That drags each satellite clock behind the ground by about 7 microseconds a day. The second comes from height. 20,000 kilometers up, Earth's gravity has thinned out, and in weaker gravity, time runs faster. That pushes each clock ahead by about 45 microseconds a day. The two effects fight. Gravity wins, by more than 6 to 1. Every GPS satellite gains roughly 38 microseconds a day on every clock down here. 38 millionths of a second. It sounds like nothing. Multiply it by the speed of light, and it becomes 10 kilometers of positional error, accumulating daily. If the engineers had assumed time is the same everywhere, satellite navigation would drift 10 kilometers in the first 24 hours and be useless before the end of the week. They did not assume that. Those clocks are deliberately manufactured to tick at the wrong rate on the ground, so that once they reach orbit, they tick correctly. The correction is welded into the hardware. Every time your phone finds you, it is confirming that time runs at different speeds in different places. Not a theory under test, infrastructure. And the natural assumption about why is wrong. Nothing is damaging those clocks. Nothing is interfering with the mechanism. An atomic clock counts the oscillations of an atom, and up there, the atom is behaving perfectly normally in its own surroundings. What has changed is not the instrument. It is the rate at which time itself passes at that location. Mass bends space-time. The closer you are to a large mass, the more stretched the fabric becomes, and the slower time runs through it. Earth is a modest lump of rock, so down here the effect is tiny, but it is not zero. It never has been. And the first people to catch it did something wonderfully unglamorous about it. October 1971. Two American scientists check in for a commercial flight. Joseph Haffel and Richard Keating are carrying 4 cesium atomic clocks. Not as freight, the clocks have their own seats, booked under the name Mr. Clock. The 4 of them fly east around the world with the rotation of the Earth. Then they do it again, heading west against it. While they are in the air, an identical set of clocks stays behind at the United States Naval Observatory, doing nothing at all but keeping time. The flights land. The clocks are compared. They no longer agree. The eastward clocks have lost time. The westward clocks have gained it. And the amounts match what Relativity predicted, within the accuracy of the equipment. 2 identical clocks. Same starting point, same finishing point. Different journeys through space-time. Different amounts of time lived. Not a difference in what the dials read, a difference in how much time actually passed. That was 1971, and the effect only surfaced because the clocks had crossed a planet. Since then, the instruments have grown so precise that the distances have collapsed. By 2010, a team at the National Institute of Standards and Technology could see the difference between 2 optical clocks separated by 33 centimeters of height, about a foot. Lift one clock the length of your forearm above the other, and it begins to run fast. The same group caught the other effect at human speed, not spacecraft velocities. They detected time dilation in a clock moving at less than 10 meters per second, roughly a person sprinting. When you run for a bus, you are, very slightly and entirely genuinely, aging more slowly than the people standing still on the pavement. And 15 kilometers above all of it, the universe has been running this experiment on its own since long before anyone was here to notice. Up there, a cosmic ray strikes an air molecule and shatters it. Out of the wreckage comes a particle called a muon. A muon is unstable. Left alone, it survives about 2 millionths of a second before it decays. Even moving at nearly the speed of light, that should carry it 600 meters. It has 15 kilometers of atmosphere beneath it. Almost none of them should ever reach the ground. They reach the ground constantly. Detectors at sea level catch them by the thousand. Several are passing through your body as you listen to this. They survive because they are moving fast, and for something moving that fast, time runs slow. From the muon's point of view, it lives its ordinary 2 millionths of a second and dies on schedule. From ours, it lasts far longer than it should and crosses 15 kilometers it had no business crossing. Both accounts are correct. They simply belong to different clocks. Time is not universal. It bends with gravity. It stretches with speed. It differs between your head and your feet. And every piece of satellite navigation on Earth is built around that fact. That is the easy part, because if clocks in different places run at different rates, then the question of what is happening right now somewhere else stops having a clean answer. 2 lights at opposite ends of the galaxy. You are drifting between them, and from where you sit, both switch on in the same instant. Simultaneous. A second observer passes you, moving steadily in one direction. She takes the same measurement, carefully, with better equipment than yours. She finds the first light came on before the second. A third observer passes, moving the other way. He finds the opposite. The second light came first. None of them has made an error. No faulty instrument, no sloppy technique, nothing to correct. Relativity says all three are describing the same universe accurately, and no experiment anyone can perform will decide which of them holds the true version, because there is no true version. Not hidden, not unmeasured. There simply isn't one. What order distant events happen in depends on how you are moving. You have spent your entire life assuming that now is a thing, a thin sheet of the present sweeping forward, containing everything happening everywhere at this instant. Your kitchen and Tokyo and the far side of the moon and a star in another galaxy, all sharing one moment. That sheet is not out there in the world. Every observer cuts the universe into their own version of now, tilted slightly differently by their motion, and no cut is more correct than any other. Even here, in this room, the now you experience is assembled from things that already happened. The sunlight on your skin left the sun 8 minutes ago. The face of someone across the table reaches you a few billionths of a second late. Your brain gathers signals arriving at different times and stitches them into a single present that never existed anywhere except inside your head. The present moment is not a feature of the universe. It is a feature of your point of view. And that leaves something the next chapter has to deal with, because it does not go away no matter how carefully you phrase it. If my now contains events that yours does not, and neither of us is wrong, then those events have to be there. All of them. Everyone's. Already. Two philosophers noticed the same thing at almost the same moment, working separately, in the mid-1960s. Their argument is short enough to state in a paragraph, and once you have followed it, it is very difficult to put back down. Whatever is real for me is real. Whatever is real for you is real. And if my present includes an event that yours does not, that event cannot be waiting in some warehouse of things that have not happened yet. Because for me, it is happening. It has to exist in order to be included. Now run that for every observer in the universe, moving in every direction at every speed. Between them, they include everything. Every event that has ever occurred or ever will occur falls inside somebody's present. Which means all of it exists. Not one moment at a time, all at once. To feel how absurd this becomes, walk down a street. Two people passing each other on a pavement, going opposite ways at an ordinary walking pace. Nothing exotic. No spacecraft, no near light speed anything. One is strolling roughly toward the Andromeda galaxy, 2.5 million light-years away. The other is strolling roughly away from it. Because they are moving relative to one another, their two versions of the present are tilted very slightly differently. On this pavement, the tilt is far too small to notice. But tilt a plane by a hair and follow it out for 2.5 million light-years, and the gap at the far end becomes enormous. For one of them, a particular event in Andromeda has already happened. For the other, walking the other way at the same speed on the same street, that event is still days in the future. Same pavement, same second. Two people close enough to touch who disagree about whether something has occurred yet. And there is no arbitration. You cannot ask which of them is correct because relativity provides no mechanism for deciding. Their disagreement is not about information or delay or perspective in the loose sense. It is about what exists. The picture physicists reach for is called the block universe. Stop imagining the universe as a three-dimensional place that changes as time passes. Imagine instead a single four-dimensional structure containing every event that has ever happened or ever will, laid out permanently in its own coordinates. Nothing in it moves. Nothing in it changes. Change is not something the block does. Change is something you find when you look along one of its directions. In that picture, you are not an object traveling through time. You are a shape inside the block. A long, thin thread running from one end of your life to the other. Physicists call it a world line. With your birth at one end and your death at the other, and every moment you have ever lived strung out along it. All of them there. All of them permanent. And the two pedestrians become simple geometry. Each of them slices that four-dimensional structure into now at a slightly different angle. Neither slice is the true one. There is no true one. The block does not come with a preferred way of being cut, which is not a technicality. Your childhood has not disappeared. It is still there, at its coordinates, exactly as real as this moment. Every conversation you have forgotten is still occurring at the place in the block where it occurred. Nothing is deleted. The past is not gone. It is behind you, the way the last town is behind you on a road. You cannot reach it. It did not stop existing when you left. And the same must be true of the future. Your death is not waiting to be created. It is not a possibility that will be resolved. In this picture, it is already there, at a specific location, as fixed and as real as your first birthday. You simply have not arrived at that part of yourself yet. Whether that is a comfort or the most disturbing sentence in physics seems to depend entirely on the person hearing it. For one man, it was a comfort. We know because he wrote it down. Princeton, March 1955. An old man, ill, sits down to write a letter. Michel Besso had been Albert Einstein's oldest friend. They met as students in Zurich and argued about physics for more than 50 years. Besso was the only person Einstein thanked in the 1905 paper that introduced special relativity, the paper that started all of this. Besso had just died, and what Einstein offered the family was not the usual consolation. He told them Michel had departed this strange world a little ahead of him, and that this meant nothing, that people like them, who believe in physics, know the division between past, present, and future is only an illusion, however stubborn and persistent that illusion may be. He was using his own theory to comfort grieving people. Not as a metaphor, he meant it as physics. Besso had not stopped existing. He was somewhere else in the block, at his own coordinates, permanently. Einstein died 4 weeks later. Now a boundary has to be drawn, and drawn clearly, because everything in this chapter has been interpretation. Relativity is measured. That is not in question. What is in question is what relativity implies about existence. The block universe is one reading of the mathematics. It is elegant, widely held, and a great many physicists regard it as simply what the equations are saying. But nobody has ever performed an experiment that distinguishes a universe in which all moments exist from a universe in which only the present is real, and relativistic effects merely make our measurements disagree. There is no test. Not yet, and possibly not ever. When a documentary tells you the future already exists, it is describing an interpretation, not a result. And there are serious physicists who think that interpretation is a mistake, and who have arguments rather than feelings. We will hear from them. They get the last chapter of this film. But even taking the block entirely at face value, one thing about it does not fit. If every moment sits there permanently, equally real, in a structure that does not change, nothing about that structure explains what it is like to be you right now. It does not explain why this particular moment feels lit up while the others do not. It does not explain memory, which reaches in one direction and not the other. It does not explain why you can recall breakfast and not dinner. The block is perfectly symmetrical. Your life is not. Something has to account for the difference. And when physicists go hunting for the source of that one-way flow, the thing that makes the past, they do not find it in relativity at all. They find it somewhere far stranger. Not in a law. In an accident at the beginning of the universe. A glass leaves a hand. It falls, strikes a stone floor, and comes apart. A white crack of sound, fragments skidding away across the tiles, one long shard spinning to a stop under a chair. Now run the film backwards. The shard lifts off the floor. The fragments race inward across the tiles, gather, seal themselves into a smooth, unbroken curve of glass, and leap upward into a waiting hand. Everyone watching knows instantly that something is wrong. A child knows. Nobody has to be told which version is the real one. So here is a question that sounds simple and is not. Which law of physics does the backwards version break? None of them. Take two of those fragments colliding in midair. Momentum is conserved. Energy is conserved. Newton's laws are satisfied exactly in both directions. Film two billiard balls striking each other, run it backwards, and a physicist watching the footage cannot tell you which way round it was shot. Nothing in the mechanics distinguishes them. And this is not a quirk of billiard balls. It runs all the way down. The equations governing electricity and magnetism work equally well with time running either way. So do the equations of general relativity. So does the central equation of quantum mechanics. Write down every fundamental law we have, reverse the direction of time in all of them, and they go on describing perfectly legal physics. There is one known exception, and it deserves naming precisely because it is so small. In 1964, two American physicists studying the decay of certain exotic particles found a tiny asymmetry, a process that does not behave identically when time is reversed. A genuine discovery. It won a Nobel Prize. It is also fantastically rare and fantastically weak, involving particles that play no part in your kitchen, and nobody thinks it is why your coffee goes cold. At the level of fundamental law, there is no past and no future. There is only a direction, and the equations are indifferent to which way you travel along it. Yet nothing in your experience is indifferent. The glass never reassembles. The coffee never heats itself. You have never once remembered tomorrow. Where does that come from if it is not in the laws? Vienna, the 1870s. A physicist named Ludwig Boltzmann works out the answer, and it remains one of the great pieces of reasoning in science, largely because it explains a fact about the universe using nothing but counting. Entropy, Boltzmann realized, is not a substance. It is not a fluid that leaks out of things. It is a number, and the number is a count of possibilities. Go back to the glass, but think about the atoms. There are a certain number of ways those atoms can be arranged and still constitute an intact drinking glass sitting on a shelf. That number is enormous, and it is nothing at all beside the number of ways the same atoms can be arranged as fragments scattered across a floor. Both arrangements are permitted. Both obey every law of physics. There are simply overwhelmingly more of the second kind. So when atoms are jostled, they wander. And wandering, they end up in the vastly larger category. For the same reason a shuffled deck comes out disordered. Not because disorder is preferred, because there is more of it. That is the second law of thermodynamics. Not a force, nothing pushes. Arithmetic, the overwhelming numerical superiority of messy arrangements over tidy ones, applied to a universe of restless particles. Boltzmann spent much of his career being attacked for it. A significant part of the physics establishment of his day did not accept that atoms existed at all, and here was a man building the foundations of thermodynamics on their statistics. He died in 1906 before the argument was settled decisively in his favor. His formula for entropy is carved on his gravestone in Vienna. And that beautiful argument has a flaw that took decades to be taken seriously. The counting does not know which way time points. Look at it again. Given a state of moderate order, the overwhelming majority of nearby possibilities are more disordered. Therefore, the system moves toward disorder. But nearby is symmetric. The argument runs just as strongly backwards as forwards, which means the same reasoning that correctly tells you your coffee will be cold in an hour also tells you with equal confidence that it was cold an hour ago, that the fragments on the floor were previously an even more scattered mess which spontaneously gathered itself into shards, that the tidy low-entropy past you remember is astronomically unlikely and almost certainly did not happen. Run statistical mechanics backwards and it predicts a past that never existed and denies the one that did. This is not a small problem. It is a direct contradiction between our best account of why time has a direction and the entire content of human memory. There is exactly one way out, and physicists took it because nothing else was on offer. You assume it. You add by hand a separate statement derived from no law, that the universe began in a state of extraordinarily low entropy, astonishingly ordered. Then everything works. The arrow points forward because we are still, 14 billion years later, sliding away from that beginning. Physicists call it the past hypothesis. It is not a discovery. It is an assumption bolted on that makes the numbers behave. Roger Penrose tried to work out how special that beginning had to be, how narrow a target the universe hit when it started. His estimate is a number that cannot really be spoken. The odds are 1 in 10 raised to the power of 10 raised to the power of 123. The exponent alone has more digits than there are atoms in the observable universe. You could not write the number down. There is not enough matter in existence to print the zeros. So look at what that leaves. Every asymmetry you have ever experienced, that you remember your childhood and not your death, that eggs break and do not unbreak, that causes come before their effects, that you are getting older and not younger, that the past feels fixed and the future feels open. All of it, every last piece, traces back to one thing. Not a law, not a force, not a principle anyone has been able to derive. A boundary condition, a peculiar, absurdly improbable initial state at the beginning of the universe which nobody has explained, and which physics simply assumes because without it nothing else makes sense. The direction of time is not built into reality. It is inherited, which is a strange enough place to arrive. But notice the pattern forming across these 3 chapters. Relativity took the present moment and showed it was a matter of perspective. Thermodynamics took the flow of time and revealed it is not a law at all, but something borrowed from an accident at the beginning. Time has been losing pieces of itself for 100 years. And then, in the 1960s, physicists attempted the most ambitious thing anyone had tried. A single equation describing the entire universe, gravity and quantum mechanics together, everything at once. They succeeded, and when they looked at what they had written, time was not there. Modern physics rests on 2 theories. Both are magnificent. They do not agree about what time is. Take general relativity first. There, time is not a backdrop. It is part of the furniture, woven together with space into a single flexible fabric that stretches, curves, and sags around whatever matter is lying in it. Time is a participant. one of the things the theory is about. Put a heavy object somewhere, and time near it slows, because time is a property of that region, not of the universe as a whole. Now take quantum mechanics. There, time is the exact opposite, a parameter, a number appearing in the equations to mark the progress of everything else. It ticks along uniformly, unaffected, indifferent to what the system is doing. It is not a property of anything being described. It is the stage the description happens on. These are not two slightly different accounts of one idea. They are contradictory claims about what kind of thing time is. One says time is inside the system, bending with it. The other says time is outside the system, unbending, absolute. Every other disagreement between our two great theories is a technical problem. Difficult, but the sort of thing mathematics eventually grinds down. This one is different. Before you can write a single line, you have to decide which of the two is telling the truth about the most basic quantity in the equations. For most of physics, you can dodge it. Gravity is so feeble at the scale of atoms that quantum physicists ignore it entirely. Quantum effects are so slight at the scale of planets that relativists ignore them just as safely. The two theories rule different territories and rarely meet at the border. But there are places where both matter at once. The center of a black hole, where an enormous mass is crushed into a region small enough for quantum physics to dominate, and the first instant of the universe, when everything that exists was compressed into that same regime. To say anything about those places, you need a theory containing both, and you cannot build one without answering the question first. 1967. An American physicist named DeWitt writes down a candidate. DeWitt had spent years on how to apply quantum mechanics to gravity, which almost nobody considered a serious career at the time. The story that gets told is that he and John Wheeler thrashed it out during a layover at an airport, and that DeWitt produced the equation shortly afterwards. He was never entirely happy about having his name attached to it. By several accounts, he took to calling it that damned equation. What he did was simple to state and audacious to attempt. Ordinary quantum mechanics describes a system, an atom, a particle, a molecule, sitting inside a larger world, with a clock on the wall outside it. DeWitt asked what happens if you remove the outside. If the thing you are describing is not an atom in a laboratory, but everything there is, the whole universe treated as a single quantum object. There is no outside for a universe. Nothing surrounds it, nothing contains it, and crucially, nothing external is available to keep time for it. He wrote the equation down. In standard quantum mechanics, the central equation tells you how a system's state changes as time advances. Feed in the state now, and it hands you the state a moment later. Time appears explicitly on one side of the equal sign, driving everything forward. DeWitt's equation for the universe has that side equal to 0. There is no time variable in it. Nothing advances. The mathematical object describing the state of the entire universe does not change, because there is nothing for it to change with respect to. This is easy to hear as a smaller claim than it is. Not that time is slow somewhere. Not that time is relative to the observer. Not even that time might emerge from something deeper. The deepest equation anyone has written for the universe as a whole describes a structure that does not evolve. Static, frozen, complete. And the most unsettling part is that nobody chose this. Nobody decided to remove time. It fell out. General relativity does not contain a preferred external clock. That was its great insight, established decades earlier. Time in that theory is internal, local, bound up with the geometry. So when you take relativity seriously and apply quantum mechanics to the whole of it, there is nowhere for an external time parameter to live. It has no address. It vanishes from the mathematics on its own. The timelessness was not imposed on the equation. It was inherited from the physics that produced it. Physicists call this the problem of time, and it has been open since 1967, nearly 60 years. Not obscure, not fringe. It sits directly in the path of any theory attempting to unite gravity with quantum mechanics, which is the central unsolved problem in theoretical physics. There are 3 ways to respond, and the rest of this film lives inside the argument between them. The first is to take the equation at face value. If it says the universe does not change, perhaps the universe does not change. Perhaps timelessness is the truth, and our overwhelming sense of flow is something else entirely, a feature of creatures like us rather than a feature of reality. The second is to conclude the equation is simply wrong. Quantizing gravity this way may have been too naive. The mathematics may be incomplete, and a better theory, when someone eventually finds it, will hand time back. The third is subtler, and it is the one that matters for what happens next. Perhaps time was never supposed to be a background at all. Perhaps asking what time it is for the universe is a broken question, in the way that asking what is north of the North Pole is broken. On this reading, time is not a thing the universe moves through. It is relational, something existing only between parts of a system. One piece of the universe changes, another piece changes alongside it, and time is nothing more than the relationship between those two changes. By this reading, the equation is not saying nothing happens. It is saying nothing happens overall. Inside, relative to each other, things change constantly. There is simply no master clock outside it all, because there is no outside. That third answer has a property the other two lack. It makes a claim you could, in principle, check. Take a quantum system, seal it completely so nothing outside can influence it and no external clock can reach it. Then look inside and ask whether a workable, self-consistent time can be built purely out of the relationships between its own parts. If it can, relational time is not philosophy. It is something a laboratory can produce. The obstacle was always obvious. Every experiment ever performed sits inside a laboratory, which sits inside a building, on a planet, with clocks everywhere. To genuinely test the idea, you would need a system utterly sealed from the outside world, with its own internal dynamics. A universe in miniature, with its own beginning and its own end, and no clock anywhere near it. For nearly 60 years, that was a thought experiment. Nobody could build one. Then somebody did. Colder than anything that has ever occurred anywhere in nature without a machine to force it. No accelerator, no telescope, no collaboration of 3,000 people, a table, in a room, and one physicist named Giovanni Barantini. The paper appeared in July 2026 in a journal called Physical Review Research, and its title is about as direct as physics titles get, testing the problem of time with cold atoms. 3 conditions had to be met at once, and each of them is difficult. The system had to be genuinely isolated, sealed so completely that nothing outside could reach in and influence it. It had to have its own internal dynamics, something actually happening inside. And no laboratory clock could be allowed to touch it, because the entire point was to find out whether it could keep time on its own. At a few billionths of a degree, atoms stop behaving as a crowd of separate particles. They fall into step. The whole cloud begins behaving as a single coherent quantum object, which is precisely what you need if you intend to treat it as a universe rather than as a gas. Then Barantini divided it. 2 laser beams of different frequencies formed a thin barrier through the cloud, splitting it into 2 regions, one bright and watchable, one dark and not. And inside that sealed little world, something began to happen. The bright region started to expand. It grew, reached a limit, and contracted again. Then it expanded once more, over and over. Atoms flowing across into the dark and back. The visible portion of this tiny, sealed universe swelling and collapsing on a repeating cycle. Which, if you squint, is a familiar shape. An expansion from a small, dense beginning, followed by a contraction back down. A big bang and a big crunch, running in miniature, on a bench in the Midlands. But the cycling was not the discovery. The cycling was only something for the clock to measure. Because the system was sealed, no information from outside could get in. Which meant that if you wanted to know what order things had happened in inside that little universe, you could not consult the clock on the laboratory wall. Not the clock in the building, not the one on the physicist's wrist, not any satellite overhead. None of them were available. Any account of the sequence had to be assembled entirely from within. So Barentini assembled one. He reconstructed the order of every event inside that miniature universe using nothing but the atoms themselves, specifically from how spread out they were, from how the disorder inside shifted as atoms crossed between the bright region and the dark, from entropy, the same quantity we met 2 chapters ago, doing a job nobody had asked of it before. He calls the result entropic time. And the striking thing is not that he produced a number, it is that the number behaves like time, properly, in every way you would want it to. It runs in one direction, giving a clear and consistent arrow without anyone having to impose one. It orders events correctly, through the expansions, through the contractions. Even as the little universe reverses direction, the sequence stays coherent. It speeds up and slows down depending on how the disorder inside is redistributing. A universe in which a great deal is changing runs fast. A quiet one runs slow. And when the distribution of particles stopped changing, time stopped. Not slowed, not became difficult to measure, stopped. With nothing happening inside the system, there was no time inside the system. Because in this picture, time was never anything other than the happening. Then Barentini did the thing that turns an interesting observation into physics. He showed that the central equation of quantum mechanics, the one that predicts how a system will behave, can be rewritten using entropic time in place of the ordinary kind. And it still works. It still makes correct predictions about what the atoms will do. This is not a curiosity running alongside real time. Inside that system, it is a functioning replacement for it. His own description of what he had shown was careful and worth quoting close to exactly. It provides, he said, the first controlled experimental evidence that time can be defined by changes within a system rather than as the external ticking clock we think of as time. And this is exactly the point where a documentary can quietly cheat, so the boundaries need saying out loud. This is not proof that time is an illusion. Nobody has demonstrated that. It is not proof that the equation from the last chapter should be read literally, or that the universe is genuinely frozen. And it is not the universe. It is 24,000 atoms in a sealed trap, deliberately simplified, chosen precisely because it was small enough to control. Nobody involved is claiming otherwise. What it is this. For nearly 60 years, the idea that time might be relational, that it might exist only in the relationships between parts of a system, with no master clock anywhere, was an interpretation, a way of reading an equation, something to argue about at a conference and go home from unchanged. It is now something that has been made, built, sealed, and observed, producing a working internal time out of its own dynamics, with no external clock available anywhere. The idea survived contact with an apparatus. That is not a small thing. A great many beautiful ideas in physics do not, and the approach opens a door. The same technique, a sealed quantum system standing in for a cosmos, could be extended to model the conditions of the early universe, or a collapsing one, or a simulated black hole. Questions attacked only ever with mathematics might now be attacked with equipment. Which brings us to two men who have been waiting a very long time for this. Both spent their careers arguing that physics has been carrying an unnecessary passenger, that time is not fundamental, that it does not belong in the deepest description of reality, and that the sooner it is removed, the sooner the remaining problems come loose. For decades, they were the eccentric wing of theoretical physics, respected and largely humored. They now have an experiment that goes their way. They agree on the headline and almost nothing else. Both think physics has been carrying time around unnecessarily. Both think the deepest description of reality does not contain it. But they arrived from opposite directions. They mean genuinely different things, and one of them goes considerably further than the other. Start with the man who goes furthest. A farmhouse in Oxfordshire, a desk, Russian scientific journals stacked beside it, waiting to be translated into English for a fee. Julian Barbour was born in 1937, and early in his career he made a decision almost nobody makes. He left the university system deliberately and stayed out. His reasoning was practical rather than romantic. An academic career demands a steady output of publishable results, which means choosing problems solvable on a schedule. Barbour had become interested in a question that could not be solved on any schedule, and he suspected that inside a department he would slowly be pushed toward easier work. So he translated Russian physics to feed his family and thought about the nature of time from that farmhouse, largely alone, for the better part of 30 years. The book arrived in 1999. He called it The End of Time. His claim is the most radical position anyone holds in serious physics, and it needs stating precisely because the softer versions get mistaken for it constantly. Barbour does not say time is relative. He does not say time emerges from something deeper. He says there is no such thing. What exists in his picture is a vast and timeless collection of possible configurations of the universe. Every arrangement the contents of reality could take, every position of every particle, sitting there as a permanent landscape of possibility. He gave it a name, Platonia. Nothing in Platonia happens. No configuration comes before or after any other. They do not queue. There is no ordering because ordering requires time, and time is the thing he has removed. So then the obvious question, if nothing is happening, why does it so overwhelmingly seem to? His answer is the cleverest part of the argument. Some of those configurations contain structures that encode what looks like a history. A fossil in rock, a photograph in a drawer, a ring inside a tree, light arriving from a star, a brain holding a memory. Each of them a piece of the present that appears to point backwards. Barbour calls these time capsules, and his claim is that you are inside one right now. This instant, the whole of it, everything that exists at this moment, including every record and every memory, is a single configuration. It contains structures implying a past, and the powerful sense that you came from somewhere, that you traveled here through a sequence of moments, is simply what it is like to be a configuration full of records. On this reading, your childhood did not happen. It is implied. The evidence is here, complete, in the arrangement of things now. It is an extraordinary position, and most physicists do not hold it. But it should not be mistaken for crankery. Barbour's earlier technical work, developed with the Italian physicist Bruno Bertotti on how to build mechanics without any absolute background, using only the relationships between objects, is genuinely respected. It fed directly into the theory that occupies the second half of this chapter, which brings us to the insider. Carlo Rovelli is Italian, born in 1956, and an outsider by no measure at all. He is one of the founders of loop quantum gravity, one of the two leading candidate theories attempting to reconcile gravity with quantum mechanics. A working theoretician with a substantial technical record, and, unusually for a physicist, a very good writer. His book, The Order of Time, sold in numbers theoretical physics books are not supposed to sell in. His position is subtler than Barbour's, and correspondingly harder to argue with. Rovelli does not say time is nothing. He says time is not fundamental, that it does not appear in the basic layer of reality, but arises from it, the way temperature arises from the motion of molecules. Temperature is real. You can burn yourself on it. But there is no temperature in a single atom. It is a property that only exists once you have a great many things and stop tracking them individually. He thinks time is like that. And underneath, he argues, the world is not made of what we assume. We picture reality as a collection of objects that persist, to which things happen. Rovelli says that has it backwards. The world is a collection of events, happenings, processes, interactions. A stone looks like a thing only because it is a very slow event relative to you. Stand back far enough in time, and the stone is a brief flicker, like everything else. So why does time feel like it flows? Because of what we are, he says. We are large, warm, and forgetful. We cannot track individual molecules, so we perceive an averaged, blurred version of the world. And the arrow of time, that absolute feeling difference between past and future, appears in the blur. A feature of our vantage point, not of the universe. He and the mathematician Alain Kahn put a formal version of this forward in 1994. Their proposal, which they called the thermal time hypothesis, was that time is not a fundamental input at all, that it emerges out of the statistical, thermodynamic state of a system. Where there is a thermodynamic state, a flow of time appears with it. Where there isn't, there is no time to speak of. That was 1994. A mathematical proposal about the deepest structure of physics with no obvious way to test it. 32 years later, a sealed cloud of atoms on a laboratory bench produced a working internal time out of exactly that. Out of its own thermodynamic state, with no external clock anywhere in the picture, which is a remarkable thing to happen to an idea. But be careful how much weight it carries. What the experiment supports is that relational internal time is coherent, that it can be constructed, that it behaves properly, that a system can genuinely keep its own time. That is closest to Rovelli's position, and it is real support. What it does not do is show that fundamental time is absent from the universe. Barbour's claim is far stronger than anything demonstrated in any laboratory, and he would be the first to say the work is not finished. An experiment showing that time can emerge is not an experiment showing that time is only ever emergent. So the timeless camp has had its best week in half a century. Two positions, one radical and one measured, both pointing the same direction, and now with the first piece of laboratory evidence anyone has been able to hand them. There is a physicist who thinks every step of this is a mistake, not a small one. He thinks it is the deepest error in modern science, a wrong turn taken 400 years ago that physics has been compounding ever since. He helped build loop quantum gravity. He and Rovelli developed it together, working side by side in the late 1980s. Same theory, same equations, opposite conclusion about the most basic question there is. And his argument is not sentimental. Lee Smolin published his answer in 2013, and the title alone tells you where he stands. Time Reborn. His argument makes no appeal to how time feels, or to intuition, or to common sense. It is an argument about method, about a habit physics acquired 400 years ago, which has worked so well for so long that almost nobody notices it is a choice. Here is the habit. To do physics, you take a piece of the world and cut it out. A pendulum, a pair of colliding particles, a planet and a star. You isolate it, ignore everything else in the universe, and describe what remains using mathematics that does not itself change. The equation for a pendulum is not younger on Tuesday. It sits outside the system, timeless, while the system moves. This is the single most successful technique in the history of human thought. Every result in this film came out of it. But look at what it requires. It requires an outside, the rest of the universe, which you have set aside. It requires repetition so you can run the experiment again and check. And it requires a clock external to the thing you are studying. Now try to apply it to everything at once. There is no outside. There is nothing to set aside because you have already included it. There is no second universe to compare against and no possibility of running this one again. There is no external clock because there is no external anything. Every condition the method depends on fails simultaneously the moment you scale it up to the cosmos. Smolin's claim is that physics did it anyway, that we took a technique built for describing pieces of the world and applied it to the whole of it, without checking whether that was legitimate, and that the timeless universe waiting for us at the end is not a discovery about reality. It is the shape of our own method reflected back. We built a tool that removes time in order to study things. Then we pointed it at everything and were astonished to find no time in the results. And he takes it further because he thinks something real is lost. If time is not fundamental, the laws of physics must be eternal and fixed. They cannot have come from anywhere. There is no explaining why they are these laws rather than others, because explanation requires a before, and there is no before. Physics simply has to accept them as brute facts, handed over free at the beginning, and stop asking. But if time is real, laws can have a history. They can change. They can be the outcome of a process rather than an assumption at the start. A universe in which the laws themselves evolve requires genuine time to evolve in, and it turns the deepest question in physics from something unanswerable into something with a possible answer. That is why he will not let it go. It is not nostalgia for the passing moment. It is that a timeless universe is one where the biggest question has to be abandoned. He is not alone. George Ellis is a South African cosmologist who wrote the foundational text on the large-scale structure of space-time with Stephen Hawking. Not a peripheral figure objecting to relativity, he helped build the mathematics. Ellis argues for what he calls an evolving block universe. The past, he says, is fixed and real, settled, unchangeable, exactly as the block picture describes. But the future is not there yet. Nothing is waiting at those coordinates. In his picture, space-time grows. It is not a finished structure we are moving through. It is a structure that gets larger, event by event, as things happen. The present is the surface where the indeterminate becomes definite. And that growth is not an illusion. It is the most important thing that occurs anywhere. And the philosopher Tim Maudlin makes the point that is hardest to argue around. Every experiment ever performed took place in a sequence. The apparatus was built, then the button was pressed, then the result was recorded. Every paper cited in this film was written after the work it describes. Every measurement in every laboratory on Earth happened in an order, one thing and then the next thing. Science itself is a temporal activity. It observes, then tests, then revises. Take the direction out of that, and there is no observing and no revising, only a static pattern that happens to contain what looks like enquiry. A physics that cannot account for the order in which its own results were obtained is not transcending the problem. It is leaving something out. So the argument stands roughly where it has stood for a century. Two camps, the same equations, better equipment on both sides, and no resolution anywhere in sight. One camp says the timeless structure is real and the flow is the illusion. The other says the flow is real and the timeless structure is the abstraction. For most of the last 100 years, that difference has been philosophical. Both sides make identical predictions about every experiment that has ever been run, which is precisely why nobody can settle it. But there is one place where the disagreement stops being about interpretation. Follow both views forward, not for billions of years, but far, far past that, out to the last stages of the universe, and they do not agree about what happens. One of them says time simply continues, whatever else is left. The other says it runs out.